So I think it's fortunate that I'm going right after Professor Martinez because I'm also in the computer systems laboratory. I'm also a computer engineer. I also think it's one of the best subfields within ECE. So this is a picture which kind of explains what Professor Martinez was mentioning. I'm going to talk about two different trends which motivate my research and kind of what we do in my research lab. So the first one is this trend towards multi-core, which is what Professor Martinez said. So this is showing mainstream processors, so what you would find in kind of high-performance workstations or servers over several decades, and it's showing a variety of different metrics. It's showing how many transistors there are per processor die. It's showing the sequential processor performance, the clock frequency, the rate at which we do execution on the chip, how much power it consumes. And what you'll notice is for a long time, for several decades, this is a log plot. We're essentially riding an exponential curve. So does anybody know what this is called? The fact that this red line goes up linear on a log plot, the number of transistors per die. It's got a famous name. Right, so this is called Moore's Law. It's not really a law at all. It's just an observation. And so what that observation says is that the number of transistors per die doubles about every 2 years. And industry is really hard to keep up with that trend. And for a long time, Moore's Law meant that sequential performance, clock frequency, all scaled up linearly as well, or exponentially as well, and that was great. But if you look here, this orange line is also going up, right? And so that's bad. So power consumption affects things like heat, cooling, cost of your system. And so essentially what happened about around 2005, you hit this kind of power wall, right? It's not really a wall. It's more of a kind of economic constraint. You want to basically consume more than maybe 120 or 130 watts in a server, you have to move to more exotic cooling, like liquid cooling or some other kind of exotic way to cool down the chip. That's very, very expensive. So purely from a cost perspective, we kind of get throttled around 120, 130 watts. And as a consequence, frequency is also leveled off, and sequential performance is also leveled off. And this, the industry, it kind of took industry a little bit by surprise, and so they threw their hands up and didn't know what to do. And so what they essentially decided is they're going to put multiple cores on a die, because the number of transistors is still increasing. So we've got plenty of transistors, we just don't know what to do with them, because we can't keep doing what we were doing. So instead, we'll take a bunch of simpler cores, we'll put them on one die, and then hopefully, computer engineers, software folks will be able to figure out what to do with all these cores. And if all that comes together, and it comes together nicely, then performance will once again start to track Moore's Law. And so right now, that was around 2005, and right now we're definitely in the thick of this. All mainstream laptops, all mainstream systems have, many cores, so up to like 4, 8, 10, and then, more aggressive systems, 32, 64 cores. So this is one trend, and just really quickly, I wanted to kind of highlight why this makes sense, why the move to multiple cores made sense. So this plot kind of motivates a lot of the research going on in my lab. This axis over here is the energy, so this is how many joules it takes to do something, like decode a video. And the x-axis is how fast I can decode a video. And any kind of computer engineering design problem you can imagine kind of being in this space somewhere. And so here we might have a very simple processor design, and we can add complexity to that processor design that'll basically improve performance, but at some energy overhead. And essentially what happened in 2005 is we bumped up against this power constraint, this red line. So really where you want to be in this space is the lower right-hand part. Because for the lower right-hand part of the space, then you're getting high performance at low energy. It's kind of like magic, right? You get it for free. And so in my research lab, what we try to look at is ways to move into the lower right-hand part of the space. And one key way to do that is specialization. So if you want to do one specific thing, you can make it far more efficient if you want to build something that can do many different things. Now, of course, the problem is it only does one thing. So what if you don't want to do that one specific thing? I can make you a video decoder which is far more efficient than any software video decoder. But what if the video decoding algorithm changes, or now I want to encode videos, or do image compression? And so that trade-off between efficiency and specialization is kind of a key theme in my group. So there's another really important trend that is basically coming like a hurricane, and nobody really knows what to do about it. And so this trend is essentially the end of Moore's Law. So we saw that exponential scaling, maybe one way to get around that is put multiple cores on the die, but sometime in the next 10 to 20 years, even, industry experts expect that we're going to have this kind of fundamental shift in terms of how many transistors are being fitted on a die. We're getting down to the point now where each switch, each transistor is getting to the size of, atoms. And there's just fundamental limits to how much we can scale them. And so this is showing kind of Moore's Law in a different way than I was showing before. And we went through all these different types of technologies, whether it be vacuum tubes or discrete transistors or integrated circuits. And there's all these different device folks looking, all these crazy different technologies, but none of them is a clear winner. And so nobody really knows what's going to happen next. And so this is kind of what this might mean is, within 10 to 20 years, architects, the people that design the systems, might be the only game in town. We might be the only ones that can really offer continued value and continued benefit. Don't tell the device guys that, because they want to basically save the day. But if they can't save the day, then we basically have to step up. All right, so what are we doing in my group? Well, the way we're trying to tackle these challenges is what I call pervasive heterogeneous specialization. So future chips we envision are basically going to be a sea of customized units in all kinds of different ways. So we might have very general purpose units. We might have units which are specialized for kind of specific types of parallel applications. We might have units which are specialized for a very specific, or maybe one or two applications. And while this, I think, can mitigate some of those trends I just said, it's kind of a nightmare from both a hardware and a software perspective, in the sense that there's all this types of variety and heterogeneity in terms of your system, and that makes it very difficult, very challenging. So more specifically, we're looking at graphics processors. We're looking at specific types of architectures, which can kind of create a nice abstraction over that hierarchy. We're looking at application-specific processors. We're looking at the interconnection network that goes on these chips that I was talking about. And I want to just highlight in more detail these two parts of what we're doing, because I think a freshman student could get involved in that over the summer. So the first one is, if we're going to have to build these really complicated systems with all this heterogeneity, it's going to be a challenge in order just to do the design work. And so one thing we're working on is more efficient and productive design methodologies. And so what we decided to do is we've used Python as a hardware design methodology. Python has a lot of nice features, which I think it makes it amicable to productive hardware modeling. And so one thing I would love for a freshman student to do is to come in over the summer and try using our framework to implement some very simple hardware designs. And then, if that goes well, get involved in the design of the framework itself. So try to improve some syntax issues, or maybe try to look at how to make it the framework itself have higher performance. And so all you would have to do is basically, if you take in CS 1.11.10, 1.1.10, if you've taken the Python introduction course, you're more than capable of kind of tackling this project. And if you've taken ECE 2300, for example, in the spring, then I think you could get involved in a different project, which would be looking at our Fpj Development Board, which is a much more sophisticated version of the board you use in ECE 2300. And you could do some projects related to taking some simple hardware designs, mapping into this Fpj Development Board, and building very simple prototypes, which in our lab, we could use as kind of proof of concepts for some of what we're doing. So again, all you really need to do in order to succeed in that project is have taken ECE 2300. So these are two simple projects which I think freshmen could get involved in over the summer.